All right, welcome back everyone to Physics Lab. So to just kind of start, let's quickly go over the syllabus. So basically we're gonna be in the room that I'm in right now. So this is 23:30. Office hours, these are in-person office hours. I don't know if we're supposed to have in-person office hours, but I guess we'll figure that out as we go through. But here they are. You can see them on here. Quick things to basically go through. Lab is very similar to what it was last semester. So basically meaning that to pass the lab, you have to get a 70% or higher out of all the lab material. And if you get a 70% or higher, but you don't actually pass the lecture portion, you can actually transfer your grade forward. So you can still use that for upcoming semester just in case you didn't pass. But same thing as before, if you don't pass the lab with a 70% or higher, then you don't pass the entire lecture. So just keep that in mind as we go through. So basically we're gonna do the same things before. So we're gonna have 11 labs and hypothetically a lab final. So this time either the lab final will be in person if we are still here on campus, or it'll be something that's gonna be virtual. So we're gonna try to actually do a lab final this time. But we have 11 labs like before. So the 11 labs were pretty much going to be the same thing as before. So it's going to be some sort of pre-lab data and then some sort of post-lab, where right now we have one formal lab report, but that may change. We have 2 lab reports, but these aren't full-fledged lab reports. They're just, pardon me. So they are just going to be basically recording of your observations, and then you're going to write them down. So this lab is a little bit different than what it was last semester, where after the first couple labs, the rest of the labs are less computational based and much more touchy-feely type, making observations and trying to discern what's actually happening based off of these observations. So here we're gonna be dealing mostly with electricity magnetism, things that we can't actually see. So by doing these, we'll get a better feeling for what these things actually are and how they actually work. So again, we have 11 labs. Again, these are all the labs. The one that we're starting today is going to be simple harmonic motion. So we'll go through this here in a second. So it gives us 11 labs, 100 points for each lab. So that's 1,100 points plus the lab final. So that's 200 points. So total of 1,300 points. Again, to pass the lab, you have to get 70% or higher. And to pass the class, you also have to get a 70% or higher. But same thing as before, since the lab grade is part of the lecture grade, then the better that the lab grade that you get, then the better that you'll be doing for the class here. So that's pretty much all about what I want to say for the lab part. Same thing as before, you'll find all the lab material basically on Blackboard. So same thing as before. So let me get off of this, come back to here. So let me bring up some of these things. Here we go. So again, under Blackboard, if we go under Blackboard, then you'll find all the lab material as before. This is also where this video is uploaded, as you undoubtedly know, because you're going to be watching this. So basically here, if you click onto the lab section, we're going to go under course content. So here we're doing simple harmonic motion lab. So click on simple harmonic motion lab. Here, this is where you'll find your pre-lab, lab. This is where you're going to upload your data and then your post-lab. Make sure you do the pre-lab before you come into lab, because again, we're only going to have an hour to basically do all the data and go through everything, which is why we're doing this video. So here to open up the pre-lab, just go ahead and click on here, and then when you're ready, just click begin. Just like last semester, you'll have 2 chances to do all of the pre-labs and post-labs. So just in case you don't get a great score your first time, go ahead and do it again. You get 2 chances. For submissions, so once you do your Excel files, then you would click on here to simple harmonic data. And then from here, you would just click on browse my computer and then upload. And then once you upload, just go ahead and hit submit. Again, anything that you're going to upload, you also have 2 chances to do, just in case you forgot something or et cetera. So again, all the same things that we had last semester. All right, so instead of beating on a dead horse, let's go ahead and talk about the lab. So hopefully this doesn't show up backwards. It looks like it's going to, which is not that great, but anyways, let's kind of quickly talk about what we're going to be doing in lab. So it looks like this is backwards. Let's see, is there a way I can flip the screen around? Oh, well, we're just gonna have to deal with it. So anyways, we'll be talking about this in class tomorrow anyways, but this lab deals with Hooke's law. So Hooke's law, from what you remember from hopefully last semester, says that the force of a spring is equal to negative, where that negative over here means that it's a restoring force, where a restoring force basically just means that it always wants to go back to its equilibrium position, times what's known as K, where K is what's called the spring constant. So that's what this guy is. And then times X, where X is a vector. This is actually a displacement vector. This is the distance it has been moved away from equilibrium. So here that direction actually does matter. And here I'm just writing it as X vector because I'm assuming that the equilibrium position is at the origin, which is X0 is equal to 0. So again, this is what we call Hooke's law. So we're going to be testing Hooke's law. We're also going to be playing with what's known as the period. So the period is the time it takes for this thing to undergo a full oscillation. So if my system starts here, goes up, and comes all the way back down to that position, that's then a full oscillation, which means that the time it takes is what we call the period. So it has to go all the way up to its amplitude, down through 0, back to negative the amplitude, and then back to 0. So that is then the period. So what are we doing in this lab? So in this lab, let me bring you over here. You can see it over here. So basically this lab is broken up into two parts. The first part of the lab is determining the spring constant of a spring. I'll show you the setup in a second. So here what you're going to do is you're going to make a bunch of measurements with a whole bunch of different masses. So you're going to plot on the horizontal the displacements. So the distance it is away from the original position, you're going to plot that in meters. And then on the vertical axis, so the independent axis, you're going to plot the force, where the force in this case is simply going to be the weight. So M times G mass has to be in kilograms to make sure that this thing is in newtons. So here you're going to make a plot and then do a best fit line. And as long as you have the force on the vertical and the displacement on the horizontal, then the slope of the line is simply equal to the spring constant. Part 2, we're then going to be playing with the period. So here you're going to measure the time, I'm calling that T50, where T50 is the time it takes for this thing to go under 50 full oscillations. So what you're going to do is watch this thing go up and down 50 times. So let's say my system starts here, here's my equilibrium. It's going to start off here, go past equilibrium, all the way up to its amplitude, go back through equilibrium down to the negative of the amplitude down here. That would then be a full oscillation. So you're going to count the number, or time the amount of time it takes for that thing to go through 50 full oscillations, which means the period then is going to be the time it takes for it to go through 50 oscillations divided by the number of oscillations, which in this case will be 50. So that will then give you the period. Okay. You're going to do this for several different masses, meaning you're going to hang some mass on here. So this mass then will be the amount of hanging mass, including the mass hanger. And then this mass that you want as well is going to be the mass of the spring. So this is our experimental setup. A little bit better here. So here we have a ring stand. This is a holder. So it's just a bar which has a few holes in it. So we're going to go ahead and put a spring through here. So this is our spring. Again, you want to measure the mass of the spring. So that's what capital M is. Go ahead and put that through here. And then we're going to put on our mass holder and then let this thing come to rest. Now, all we're going to do in part 1 then is we're going to go ahead and put some mass on here and we're going to measure the displacement away from its initial starting position. Now, how you want to do this is completely up to you. You have two basic options. One option is you can measure the distance that this thing increases from up here, for example. So what you can measure is initially this thing is what, 25 centimeters up here. And then down here, this is at roughly, so you want to go to about the bottom. So it's about 73 centimeters. So you want to know that is the initial position, 73 centimeters. And then in this case, go ahead and put on your mass. This is then going to elongate. And then you want to measure that distance then at, it's going to be roughly about 83.5, and then write that down. So either you can measure the distance from, again, up here, or go ahead and flip this guy over and then measure the distance from the floor. So if I measure the distance from the floor, and make sure this guy's not oscillating. So in this case, this is about 120 centimeters from the floor. That's my initial position, and then I'm going to go ahead and put this guy on. So once I put that on, this is now going to be about 100, once you stop oscillating, maybe about 116.5. So either way, it doesn't matter. As long as you're consistent on how you do it, it's completely up to you. So again, either measure the distance that the spring itself has elongated from the top, or measure the distance from the floor. But the more mass that you put on this thing, it's going to go over the side of the table. So make sure, as I have done here, that this thing is hanging over the side of the table, so that way when it elongates all the way down, it's not going to hit the table. So this is going to be part one. So here, again, you're just going to hang a bunch of masses on here. And again, plot the force versus the position, or in this case, the displacement. And then from there, you're going to go ahead and make that plot, and then you want to extract the spring constant by simply looking at the slope of that. Now for part two, now what we want to do is make it undergo simple harmonic oscillations. Let me move my camera over here so you can actually see a little bit better. So here, we're just going to put some mass on here. The lab manual tells me how many that we're going to put on, how many times we're going to do that. But let this thing be at rest initially. Give it a little bit of a pull down. Now the distance that you pull it doesn't matter, but try to pull it a little bit further so that way it's easier for you to count the number of oscillations. So again, if I start off here and I pull it down, this is its initial position. So I have to let it go all the way up, compress, come all the way back down to that initial position at which it started. That then is a full oscillation. So I'm just gonna go ahead and pull that guy down. Somewhere around 10 centimeters or so, that's fine. And then let it simply oscillate. So every time it hits my finger here, that is a full oscillation. So you're gonna count from here. So that'd be 1, 2, 3, 4, etc. So you're timing the amount of time it takes for this thing to go through 50 full oscillations. Once that's done, stop it, do it again. And then from there, you want to find that average. That's then going to give you the period. So the average amount of time it takes will then give you the average period. And that period then is going to simply be the amount of time it takes for it to go through 50 oscillations divided by 50 oscillations. So that's pretty much it. From there, again, we only have 1 hour to basically do all this. So you'll have to then do all the calculations probably outside of lab. You may have some time to do some of the calculations inside of the lab, but that's pretty much about it. So again, just looking at Hooke's law. So again, Hooke's law says this thing always wants to go back to its equilibrium, which means that if I pull it downward, the force in this case is going to be upward. If I then compress it in this direction, the force would then be downward, trying to get it back to its equilibrium position. So any force which causes an object to try to move back to equilibrium is subjected to this Hooke's law, which again says that the force is equal to negative, where the negative means it's restoring force, the spring constant times then the displacement. But again, if the initial position is at x is equal to 0, then it's just times the position vector where that thing happens to be. So again, first part, we're hanging a bunch of mass on here, measuring the distance, say, from the floor to the bottom of the mass hanger. So this portion down here. Again, in that case, you're just going to make a plot of the force versus then the displacement to then extract the spring constant. Once you know that spring constant, then you're going to go ahead and cause this guy to undergo simple harmonic oscillation in part 2. Try not to let it do what I have it doing here, kind of flipping around. You want this thing to be oscillating in a nice kind of straight line, so that's a little bit better. So here, again, you're measuring the time it takes for this thing to go through 50 oscillations. Do that a bunch of times for a whole bunch of different masses. Once you have that spring constant for part 1, then you'll compare the theoretical period to the period at which you just calculated to then the period at which takes the mass of the spring into account. So you're going to compare all 3 of those different ones using discrepancies and absolute and relative discrepancies. Okay. So that's it. Other than that, I'll see everybody in lab. And again, be ready to work as soon as you get in the lab. So as soon as you walk in, once the time officially starts, go ahead and start doing all of your lab stuff, taking all your data, asking any questions that you have. If you have any questions before that, go ahead and leave them in the comments below. Or you can always email me or talk to me at the beginning of the lab. Okay. So see everybody in lab.